You found the skeleton. How would you calculate that distance? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.
Hey there YouTube, the Dapper Dinosaur here. I am back with another update for the Speculative Evolution project. I have 8 or 9, depending on how you count them, organisms to show off, and so rather than stand on ceremony, let's just jump into it. First up, we have the Bathmat. Bathmats are primitive retinophytes that grow on rocks or coral skeletons. They are fast growers and a common source of food for smaller herbivores in the oceans of ancient Almaishah. Shown here, an armor globe is about to scrape some Bathmat up into its mouth. Creature design by Dapper Dino. While descended from Octocoral, Bathmats have a very attenuated form of that organism's geometric arrangement. They now simply grow to fill in cracks and crevices with little regard to forming octagonal or square segments. They have also forgone the formation of specific spore-producing pods. The most notable innovation of this clade is thin filaments containing high amounts of photosynthetic cells. These filaments facilitate chemical exchange with the water as well as maximize the surface area available for photosynthesis. Bathmats are hermaphroditic broadcast spawners. They have no particular spawning season and simply release male and female gametes periodically from their surface. They are also capable of vegetative reproduction, as if a patch of Bathmat is severed, it can grow independently into a new organism. A new Bathmat zygote will settle into a, hopefully, sunny area underwater and start to divide. Upon reaching 32 cells, it will secrete a biological cement onto the substrate and start growing towards the light and into any good cracks that can help it stay in place. Once it has a total surface area of about 3 square centimeters, it will start producing filaments. After reaching about 5 square centimeters in total area, it will start releasing gametes. Genetic ancestor? Octocoral. Scientific name? Mat balneum. Origin ancestry? Retinal phyto. Lifespan? 5 local years. Average height? 5 to 10 millimeters. Average length? 6 centimeters. Now we come to Bopheads. These bipedal megafaunal browsers vaguely resemble humans, though their intelligence is more akin to a goldfish at the very most. Creature design by Random Evo Times. Bopheads stand bipedally to get at the highest floral life around them without the luxury of a neck. They can also use their tendrils to get at food, but they are able to retract them to protect them from damage. This allows them to grow to megafaunal sizes and compete with nectonic herbivores, as well as protect themselves from most predators through sheer size. Their legs are covered in hooves of dead skin, like other herbivores at the time, to protect their feet from hazards. However, with only 2 legs, armoring them with hooves is a lot easier. They also possess a tail club made of dead skin on the end of the tail, able to withstand high forces when used to smack predators, and simple camera eyes that contain 2 types of cone cells, one that is most active with short wavelengths of visible light, the other is more active at longer wavelengths, so they are able to distinguish purple and blue foraging mates from longer wavelength emitting predators. While their bobber ancestors lacked the claws typical of pseudotetrapods, this was due to a broken promoter. In this line, the promoter was reactivated, and as a result, the forelimbs carry claws that allow bopheads to defend themselves from those predators large enough to threaten them. When the mating season comes around, groups of males coordinate to swarm around females. Each male takes his turn displaying to the female, waving his purple arms colored by their diet up and down. After this is over, the female picks her favorite male out of the bunch and they mate. The other males leave to search for another female they can mate with. The female lays her internally fertilized eggs in a tiny hole in the ground she has dug, and then promptly abandons the eggs to mate again. The juveniles are quite precocial, and they climb up on the tall retinophytes the adults feed from, and begin munching on the leaves for the first 5 local years, after which they reach full size and are sexually mature. They live in warm shallow waters, like a lot of species at this time. That means the Yamanatash Major Reef System, or YNMRS for short. Most of their diet is tall retinophytes, although floating photosynthesizers are not off the table for them, and occasional terrestrial plant runoff or ground flora wouldn't hurt them if they are eaten. Genetic ancestor, bobber. Scientific name, Dipodus dendrovorus. Origin, pseudotetrapoda. Lifespan, 12 local years. Average height, females are 375 centimeters, males 325. Body tint and coloring, males have purple-tinted forelimbs that are colored by retinol from their diet, being deposited in the dermal cells of those limbs. Females lack this feature. Now we come to the earth jelly. Earth jellies fill about the same niche in the oceans of ancient Almaishah as mysticetes on Earth. Like them, they carry with them a whole ecosystem of endosymbionts and endoparasites, essentially carrying a miniature reef system with them as they travel across the globe. Creature design by Random Evo Times. Earth jellies are still rather similar to their ecoglobe ancestors in terms of general anatomy. They have 4 large eyes, each 90 degrees from each other. They also have 8 tentacles, with 2 being different from the rest so they can nectonically swim through the water. a bell that acts like a teleos swim bladder, and gills that efficiently extract oxygen from the water. 6 of the 8 tentacles are connected by webbing which are used to capture prey. Earth jellies use the same reproductive strategy as the ecoglobes, i.e., they cluster together during the mating season. The individual tentacles tangle together and trade gametes, with the newly hatched larvae clinging to their mothers and feeding on what gets entangled on the protrusions, this time with a much higher survival rate than those of the ecoglobes, from the sheer amount of things covering the adults. They grow quickly, reaching half-adult size in 10 months, at which point they go off on their own. Just like their ecoglobe forerunners, Earth jellies are a mini ecosystem in their own right, housing a wide variety of species, even more so because of the amount of anchoring points for organisms to settle on, and the sheer size of the creature, allowing basically any reef species under 1 meter in size to settle on them. They truly live globally around the ocean, inhabiting shallow marine and open marine waters, along with being able to live in both tropical and polar temperatures. They are filter feeders as adults, thus their mouth entrances are rather small, and so they are unable to swallow anything larger than a couple centimeters. As juveniles, their mouths are much proportionally larger than the adults, making them opportunistic omnivores that eat whatever is smaller than themselves on the back of the parents, even other juvenile earth jellies. Earth jellies have webbing around most of their tentacles, and they have 2 undulating tentacles which they use to herd plankton into the net. The net widens slightly and then rapidly closes, with thousands of tiny, fine bristles lining the inside of each of the tentacles, passing food around them between the cilia until it reaches the mouth in the center of the tentacles. It then expels the water in a loud boom that can be used to scare off predators. They are found in open water worldwide. Earth jellies, as a result of mostly not having any choice, carry with them their own small ecosystem, including many species closely related to reef organisms, such as octocorals, and various modal creatures, such as rose limpets and reef fish. While they gain little benefit from most, some are harmful, and some, by feeding on the parasites, are beneficial. Genetic ancestor, ecoglobe. Scientific name, Malacocetus gigas. Origin, Xenoradiata. Lifespan, 30 local years. Average length, 4.5 meters. Now we come to a collaborative submission. We have the Jade Crown. In the wake of the mass extinction, some species embraced cooperation as a method of survival. Some species of reef crowns formed a symbiotic partnership with Cecilia. Their tentacles are hollow, allowing the phytozoans a safe place to live in exchange for a portion of the food they produce. That has led to the Jade Crowns, who form into massive colonies built on the shells of their ancestors. Creature designed by Saurus Blooded, Charid, and Dr. Misa. Physically, Jade Crowns are almost identical to reef crowns, building a calcium carbonate tube base to live in that is attached to the seafloor. Where they differ is in their tentacles. Jade Crown tentacles are larger and hollow to allow for colonies of Cecilia to live in and provide food for the Jade Crown and grant it a green color. A new development is the ability to create new Jade Crowns by budding off from the tentacles, creating a new Jade Crown directly next to the original. Over the generations, Jade Crowns can create large colonies of themselves built on the calcium carbonate shells of their ancestors. Though capable of budding, Jade Crowns, like their ancestors, practice male and female broadcast spawning. Buds will emerge as miniature versions of the adult Jade Crown, but those born due to broadcast spawning join the planktonic soup as larvae that are very similar to the basal rose crown. After a few local months, the Jade Crown will attach itself to the seafloor and begin a new Jade Crown colony. Jade Crowns prefer the shallow seas around the equator, as they require a lot of sunlight to support their Cecilia residence. They live in the shallow waters between Kupchai and Yama, as well as along the southern coast of southern Yama. Genetic ancestor, Reef Crown. Scientific name, Vidicorona insulum. Origin, Xenoradiata. Lifespan, 2 local years per individual. Average height, 1 centimeters for individuals, about 3 meters for colonies. Next up is Megacaris. These large herbivores can colloquially be referred to as tanks that look like vegan lobsters. They are large, but will only get aggressive when provoked by a predator. Creature design by Random Evo Times. Megacaris are generally just scaled up Durospina with some small differences. They have reached megafaunal size to combat the increasingly dangerous predators in the seas of Almaishah. Adding to this defense kit, they have an extreme amount of armor made from dead skin. This means that when the creature curls up, it can make it so only its armor is displayed to the outside world. Helping with this is the retractable antennae. They also display, quote, hooves made of dead skin at the end of their feet, protecting them against jagged terrain and small ground predators. Lastly, they have claws very close to the mouth that really help grind up food before digestion. Acting like a set of mandibles, along with a neck to rotate the head up or down to forage without grasping claws. Reproduction is exactly the same as Durospina. They begin as egg sacs, each containing dozens of embryos that are laid in mass by parents and then promptly abandoned. Then they use built-in instincts to find food and grow to full size in 5 local years and breed from then on. They live in shallow waters around continental shelves, except in cold waters. They live all around Kupchai, the southern tip of Arctica, all but the northern coast of Yama and in the shallow waters between Yama and Kubshai. Megacarrots are opportunistic herbivores, but generally juveniles prefer higher growing plants because of their easy to digest and energetic leaves, but adults rely mostly on low quality ground plants because of their impressively efficient plant masticating abilities. Genetic ancestor, Durospina. Scientific name, Megacarus phytovora. Origin, Paleotagmata. Lifespan, 12 local years. Average length, 350 centimeters. Now we come to a section that's kind of a 2-for-1. You see these are two very close related organisms, and so I'm combining the description for both of them into one since it's almost identical and I don't want to have to say the same thing over again in this video. But these are the octocoral species of genus Polyfungos. Brightly colored skeletal fish, eel-like ambush hunters that hide among the coral, Anomalocaris-like apex predators, and nocturnal hive-building bottom dwellers, which eat the flesh of the dead, build their nest within the bones, and who light up the sea with territorial displays of bioluminescence. They are just some of the inhabitants of the tropical octocoral reefs. Octocoral is a descendant of Octogus. It grows in polygonal segments called polys. These polys are usually octagonal in shape, however, it is not uncommon for them to grow with fewer sides. It uses a secreted adhesive to stick to rocks, and new polys sprout from the corners of the previous ones like Octogus. But unlike Octogus, octocoral grows three-dimensionally, with segments growing in all directions, often growing up towards the sun. This is thanks to its internal mineralized skeleton, which gives it a hard structure and lets it hold its shape. Each poly has a single flat polygonal bone, which is fused to the bones of the adjacent polys. Mature polys can fuse with other mature polys of the same individual if they come into physical contact. The bones of each poly are sharp and reach slightly beyond the flesh, giving each one a razor-sharp edge. This makes octocoral extremely unpalatable to all but the most specialized or determined of herbivores. Furthermore, octocoral stores very little nutrients in its tissues, due to its tropical environment giving it a constant stream of energy. This acts as a further defensive measure by making them even less palatable. The exact structures the coral will form varies from species to species. Some form roughly fractal branching tree-like structures reaching up to the sun. Others form large flat platforms made of just a few large octagonal sheets, designed to drink up the sunlight from as large a surface area as possible. Some form hollow tube-like structures, perfect shelter for small reef dwellers, who in turn fertilize the coral with their waste, and yet others form dense blob-shaped structures made of thousands of polys, densely packed polygons, almost too small to see with the naked eye. Octocoral can reproduce in three ways: asexual fragmenting, sexual fusing, and sexual budding. Fragmenting occurs when a piece of octocoral is broken off. It secretes an adhesive agent from the open wound, which dries and forms a scab on the piece still connected. But for the small broken off pieces, the adhesive means that if they are lucky, they can attach to a rocky outcrop, where they can start growing again. This can be done even with tiny pieces, as long as the piece has at least one corner of a poly on it, from which the retinal phyte can sprout a new poly. However, having more mass is helpful and can help it reach full size faster. Octocoral is heavy enough that pieces sink to the bottom, but light enough to be carried a little way by the first current. The second manner is a form of sexual reproduction. Some species of octocoral can fuse with other members of the same species should they touch, in the same way polys from the same individual can fuse to each other. This allows for a splicing, if you will, of the DNA, and polys that grow from the touching polys are genetically distinct from the two parent individuals, despite still being physically connected. However, this form of genetic splicing has been secondarily lost in most species, as it spread disease. Instead, most exclusively use their buds for sexual reproduction. This is the primary method of reproduction for all octocoral species. Mature and healthy octocoral will produce clumps of buds on the same corners of some of their polys instead of producing more polys. These clumps contain up to 100 spore-like buds inside of a protective shell. A single octocoral will have a few hundred to a few thousand clumps depending on species. When conditions are just right, all the octocorals of a species will release their buds into the current at the same time, using water chemistry, temperature, and light levels of both the sun and moon to synchronize their release with each other, filling the sea with millions of buds in one go. This overwhelms the many predators that eat the buds, as each bud has a small package of nutrients for the young coral, making them an ideal snack and making spawning a veritable feast for reef dwellers. Spawnings are loosely based on time of year, but if the triggering conditions don't happen, they won't spawn that year, and they might happen at a different time of the year or multiple times in one year if the conditions are met more than once. The buds float in the current, but should two meet, they will fuse and splice their DNA, in a similar manner to fusing adults, creating a genetically unique individual. After a few hours, the buds produce adhesive and settle to the ground, beginning to grow into new octocorals, with those that didn't fuse simply growing into clones of the parents. Once they attach to the ground, they can no longer splice DNA. This is a far safer way to sexually reproduce than fusing of adults. Octocoral grows slowly, and when growing from buds or small broken off polys, it will take a few years for it to be big enough to start diverting resources to making buds, and it will be a few more years for it to reach full size. Octocoral provides a habitat for hundreds of unique species that rely on the reefs for shelter, such as the ribfish and Thanatodon ephelos. The webs of hard poly and the caves swarmed in them are the perfect hiding spots for small organisms and ambush predators alike. The coral also supports some organisms more directly, such as the fortress mesa, who use the coral for nest materials, using broken off pieces of coral to build and disguise their nests. Octocoral requires very specific conditions to grow. Firstly, it requires a rocky attachment point, without which nothing else will matter, as Octocoral is completely incapable of growing on loose substrate like sand or gravel. Secondly, Octocoral requires constant tropical sunlight. Low light levels will stunt its growth or even kill it. Due to Octocoral storing little nutrients as a deterrent against predation, it needs a constant stream of energy to keep it alive. Even a few heavily overcast weeks in a row can cause reefs to die back substantially. pH and water hardness is also very important. Octocorals thrive in hard water with a pH from 8.2 to 8.5, and will start to die at 7.2. Events that lower pH rapidly, such as volcanic activity and the deaths of large creatures leaving behind an excessive amount of decomposing material, can cause diebacks. Combinations of pH drops and low sunlight can cause major reef die-offs that turn the purple/pink reefs bone white. Upon death, an octocoral leaves behind its skeleton. Once all other organic materials have rotted away, the skeleton is rough and porous due to the vessels and pores in it for fluid transport and storage. These rough skeletons are a perfect attachment point for more octocoral, and the skeletons leach minerals into the water, raising pH and water hardness, making it ideal for more octocoral growth, so the reefs that experience large diebacks provide the ideal environment for a new generation of octocoral. For this reason, most reefs are constantly waxing and waning over the decades. Also, because of octocoral's ability to grow from skeletons of previous generations, it is able to colonize once barren sand dunes, turning them into moderately sized reefs over the course of a century or so. All it takes is a single exposed boulder to appear and become home to an octocoral. Then the generations of octocoral will build on each other until a new reef is created. Now we come to another octocoral. The TubeOctocoral is a reef-building organism that provides a home for many other organisms, who return the favor by defending their home from browsers who might like to make its soft outside a snack. Creature design by Sean Draws. Unlike other octocorals in genus Polyfungos, Fistulafungos does not have discrete polys, and its skeleton is thin but distributed throughout its body. It grows in a tube shape, and the center of the tube is often home to some other organism. During the mating season, buds will develop at the top of the tube. These release haploid isogamous spores both into the water column as well as onto the surface of the octocoral. The former may meet other TubeOctocoral spores in the water column, while those stuck to the outside may be picked up by passing organisms and brought to other nearby tube corals. The TubeOctocoral reproduce both by fragmentation and via spores. Fragmentation occurs when a piece of octocoral is broken off. It secretes an adhesive agent from the open wound, which dries and forms a scab on the piece, still connected. But for the small broken off pieces, the adhesive means that if they are lucky, they will attach to a rocky outcrop where they can start growing again. Having more mass is more helpful than having less in this, as this can help it reach full size faster. Octocoral is heavy enough that pieces sink to the bottom, but light enough to be carried a little way by the first current. Sexual reproduction is the primary method of reproduction for all octocoral species. Mature and healthy TubeOctocoral will produce clumps of buds on the rim of the tube. These clumps will contain up to 100 spores inside a protective shell. A single octocoral will have a few hundred to a few thousand clumps. When conditions are just right, all the TubeOctocorals release their spores into the current at the same time, using water chemistry, temperature, and light levels of both the sun and moon to synchronize their release with each other. This fills the sea with millions of spores in one go, and overwhelms many predators that eat the spores. Each bud has a small package of nutrients for the young coral, making them an ideal snack, and making spawning a veritable feast for reef dwellers. Spawnings are loosely based on time of year, but if the triggering conditions don't happen, there will be no spawn that year. And a spawn might happen at a different time of year, or multiple times in one year if the conditions are met more than once. Spores float in the current, but should two meet, they will fuse and splice their DNA. Octocoral provides a habitat for hundreds of unique species that rely on reefs for shelter, such as the ribfish and the Thanatodon ephelos. The webs of hard skeletal matter and the caves formed in them are perfect hiding spots for small organisms and ambush predators alike. Genetic ancestor, Octogus. Scientific name, Fistulafungos domesticus. Origin, retinal phyta. And finally, we come to the rose limpet. The rose limpet is a scavenger and occasional predator of sessile organisms which slowly crawls its way around the ocean floors of ancient Almaishah. Pictured, a rose limpet crawls across a rock searching for the scent of food. Creature design by Dapper Dino. Rose limpets are quite highly derived compared to their reef crown ancestors. The tube of the reef crown is now just a shell which forms around the aboral end, which has now become a dorsal side. Motive tentacles have now merged into a single muscular foot on which the rose limpet walks in a manner similar to that of a snail on Earth. even exuding a mucus-like lubricant. This foot surrounds a centrally located mouth composed of 8 strong tentacles, each tipped with a hard calcified tooth-like structure made for shredding its favorite food, carrion. Inside the organism is where most changes have taken place. The rose limpet exhibits a slight secondary bilateral symmetry. It has only 4 gonads, and the whole organism is either male or female. Around the aboral nephridium is a ring-shaped ganglion which functions as a rudimentary brain, controlling the tentacles and the direction of movement of the foot. What in the ancestral rose crown were motive tentacles and in the reef crown were primarily prey capture tentacles are here used as sensory organs. They are sensitive to scent and touch, but also have a very rudimentary photosensitivity, just enough for the rose limpet to know dark from light. These may be retracted into the shell and water expelled by the foot pressing the body down. This creates a suction and makes the entire organism difficult to detach from a rock, which is its primary form of self-defense. The shell itself grows outward and down in distinct layers, and it is made of silicates similar in composition to the skeleton of a sponge. Like the ancestral rose crown or earth starfish, the gut of a rose limpet is blind, and the same orifice expels waste and takes in food. It is also the orifice used to expel gametes. Rose limpets are no longer broadcast spawners. Instead, they can determine the sex of a conspecific via scent, and when members of an opposite sex meet, they will typically mate, the female expelling a few hundred ova on the ground and then guiding the male over the deposited eggs for him to externally fertilize. Most such broods only have 1 or 2 individuals survive to adulthood, or even none, but mating occurs every few local days for any given rose limpet, so overall they tend to have a fairly high reproductive rate and can easily colonize new areas through this high rate of reproduction. Fertilized rose limpet ova will quickly grow into a small larva that resembles the ancestral rose crown, living as a planktonic predator of zooplankton. As they grow, they begin to be able to swim against the current. Once they reach about half a centimeter in length on the long axis, they will swim down to the substrate and find a crevice. At this point, they will undergo a bit of metamorphosis. They will grow a tiny shell, and the 32 feeding tendrils will shrink in length and merge into a muscular foot. When this is done, the organism will have shrunk to about 0.35 centimeters in length and will be a miniature adult. As generalist scavengers, rose limpets can be found in virtually every marine environment. In shallow waters, they will also eat organisms such as jade crowns. Despite being geniuses among stephanozoans, rose crowns have only the most rudimentary brain, and are in fact completely instinct-driven, being completely incapable of learning from experience. The tentacles of rose limpets are their primary sensory organ, although all the soft tissue is sensitive to pressure. The tentacles are highly sensitive chemoreceptors. They are finely tuned to detect chemicals released by decaying flesh. The tentacles are also extremely sensitive to touch, and the timing delay of them sensing pressures in water can alert the rose limpet to not just the presence of a larger organism moving near it, but also its direction. The last form of sensory information the tentacles provide is extremely simple photoreceptivity. This allows the organism to know roughly what time of day it is, and also if there is a sudden change of light, it may indicate a predator, provoking a defensive response. Genetic ancestor? Reef crown. Scientific name? Testaharine planus. Origin? Stephanozoa. Lifespan? 3 to 5 local years. Average height? 0.5 centimeters. Average length? 2.5 centimeters. The tint of the shell will vary based on the mineral composition of the local water. While the shell is composed of silicates, trace impurities will make their way in and change its color. Alright, well that's it for this update. As I'm sure you guys know, submissions are in fact closed, and we are working on them, both me as well as Sean Draws, and a few other people who are working with the scientific aspects of the background. I'm sorry these take a little bit longer than I would like for them to come out, but I do have a really high standard for things like the art quality and trying to make sure that everything works together. If you're worried about whether or not your submission has made it, chances are I haven't even looked at it yet, and I probably won't be giving you a heads up as to whether or not it made it. If you're worried about it, my recommendation is that if you sent it to me as a link to a doc file, update the doc file to make sure that it is exactly what I need from a submission. Follow submission template exactly, and the only other thing I can say is try to make sure that your submission actually makes sense on its own. What I would not suggest is asking me about your submission, because chances are that'll just make me put it to the back of the stack, if I'm being honest. I already work a lot of hours on these, and I don't actually have time to answer the question, did my submission make it, from everyone? Because in the last couple phases, I got those questions almost daily, from multiple people in some cases. So please don't do that. Anyway, I really hope you like this. I hope you look forward to the next one, and I'll see you next time. Don't forget to like, subscribe, and hit the share button. I'm the Dapper Dinosaur. I'd like to just take a moment to thank my channel members and patrons, especially those pledging $20 or above: Ben Tovand, Ian Chen, Chris Love, Sphincter of Doom, and The Venerable Bede. My channel members and patrons help make this a much more stable income, because as you might know, ad income varies wildly from month to month, even with the same number of views. and it really helps this channel stay on the air. But if a monthly pledge or a yearly pledge, which I have now activated, isn't right for you, there's a merch store linked in the description, and every like, share, and subscription really helps the channel grow. Also, those pledging $10 or above will have access to free 3D art assets, including materials and models, which will be made for Blender by me and can be used in any project without crediting me.
How